To wrap up this section today on the special classes matrices. So last time it was Banjo matrices. Now we're going to look at a case where A is a symmetric matrix, and then also focusing on a case where A is not just symmetric, but also what's called positive definite. So we'll find all of these things. Okay. So as we were learning here, the first year out of the course, but I just assume that students can forget anything. That a matrix is symmetric if it's equal to its own transpose. The transpose comes from just reversing the sense of rows and columns. So the ij entry of A transpose is the ji entry of A. So this is an example right here of a 3 by 3 symmetric matrix. So really you have like mirror images across the diagonal. Like these twos agree. We have these threes and then these fives. So aij is equal to aji. Okay. Now, let's suppose we're able to compute the LU decomposition. Now, it's true it might not necessarily exist, but in this case, we'll assume that it does. Of course, we have L being unit lower triangular, and U is upper triangular. So then, what I can do is I can decompose U into a product of a diagonal matrix D that has the diagonal entries of the original U, and then that we multiplied by some matrix M transpose. Now U is upper triangular, and D is diagonal, so M transpose is going to be unit upper triangular. This is the formula for M transpose right here. All I'm doing is, if I read D first, and I just take the diagonal entries of U and place them on the diagonal of D, and then otherwise D is 0. And then I take D and multiply its inverse by U. That will give me M transpose. This is something that can actually be computed. So M transpose would have to be unit upper triangular, so therefore M is unit lower triangular, so taking the transpose. So now we have a slightly different decomposition. So A, instead of saying A equals LU, we have A equal to LDM transpose, or so people refer to it as like the LDMT decomposition, which on its own, I'll just tell you right now, is kind of useless. Until the matrix is symmetric. Right, so now we have this decomposition where both L and M are unit lower triangular. Yeah, so generally no one will bother to compute this, but if it's symmetric, then I take the transpose of this equation, and I have, and I'm using the property here that the transpose of a product is the product of the transposes, but in reverse order. So that gives me MDL transpose. So if A is symmetric, then these two factorizations have to be equal.
Why do you switch it? They make it MDL transpose?
Oh, that comes from taking the transpose of this.
Okay.
And that would give me M, and then I go in reverse order. And then I get, so I transpose this, transpose D, but D is a diagonal matrix. So it's equal to its own transpose. So it just remains D. And then I have L transpose. Okay. So because A transpose equals A, I can set these factorizations equal to each other. And L and M are both units lower triangular. And as comes up in one of the homework problems, that means it's invertible. So what I'm going to do here is I'm going to rearrange this equality here. I'm going to multiply on the left by n inverse. So I'll just state what I'm doing here. On the left by M inverse, and multiplying on the right by, so what's going to be kind of weird here is I want to cancel this M transpose that's on the right. So I'm going to multiply by M transpose inverse. Okay. Now, the inverse of the transpose is the transpose of the inverse. That's something I can do directly. So when you're taking a matrix, don't take its inverse and its transpose. It doesn't matter in what order you take that. You can do inverse and transpose or transpose and inverse. The result is the same. For that reason, I want to introduce this notation. M superscript minus t. So this means inverse transpose. So we just have one symbol that instead of dealing with all these parentheses. So after doing that, then this is what I have. So D L transpose M inverse transpose equals M inverse LD. Now, when you have a situation like this, where you have a product of two matrices that are both transposed, then you can use this property. And this property I've already used, I used it up here. That the transpose of a product transpose in reverse order. So here I have L transpose M inverse transpose. So that's playing the role of B transpose A transpose right here. But I can write that as the transpose of a product by taking this is my A, and this is my B, and reversing their order. So this part right here, L transpose, M inverse transpose, is the same as M inverse L, but take the transpose of the whole thing. Questions so far? I know there's a lot of manipulations happening.
So D is A and L and M are.
In this case, role of A is being played by M inverse, and the role of B is being played by L.
Oh, and D's just there.
Yeah.
I see.
She just is hanging there watching. Now, why did I do that? Because if you look at this equation, I have M inverse L on the left side of transpose, and then I also have M inverse L on the right side. Now, let's talk structure. What types of matrices do we have here? Remember, D is diagonal, M and L are both unit lower triangular. Now, left side is M inverse L, that is unit lower triangular, because if you take unit lower triangular and you invert it, it's still unit lower triangular. If you multiply it's still by unit lower triangular, it's still unit lower triangular. Say that 3 times fast. But then I take the transpose of all of that. So on the left side I have a diagonal times an upper triangular. So the left side is upper triangular. Now we go to the right side. Well, we're using the same reasoning. M inverse L, that whole product is going to be unit lower triangular. And then I multiply on the right by D, that's the diagonal matrix. Multiplying by diagonal matrix never affects triangularity. So the right side is lower triangular. So, yeah. So if I have upper triangular equals lower triangular, and you saw this sort of thing before, when I proved that the LUT composition is unique. The same kind of argument is used. So M inverse L has to be diagonal. I mean, both sides are diagonal. D is already diagonal. Therefore, M inverse L is diagonal. But when you have a diagonal matrix that is also unit lower triangular, the diagonal is populated entirely with ones. So M inverse L is identity. So I just rearrange this and like, oh wow, M equals L. So now I have this factorization. A is equal to L d L transpose. So when A is symmetric, the two unit lower triangular matrices involved in the LD empty composition are actually equal. So this, anytime you have a matrix like this, where you have a symmetric matrix in the middle, like a diagonal matrix, and whatever you multiply with on the left is a transpose of whatever you multiply with on the right. Any matrix of this form is necessarily symmetric. So now I have a symmetric factorization of a symmetric matrix. Because we don't really want to use LU if matrix is symmetric, because that factorization, A equals LU, that has a certain asymmetry to it. But now we don't have that anymore. So if we're going to solve A equals B and A is symmetric, okay, we go ahead and compute LDL transpose, then how do we solve AX equals B? The process is very similar to what we've already seen when we do the LU decomposition. In fact, the first step is exactly the same. Do Ly equals B, that's forward substitution. And then what we used to know of as Ux equals Y, back substitution, is broken down into two stages. First, you handle the diagonal. So you solving a diagonal system just by dividing by the diagonal entries of T. And then you have solve a unit lower triangular system involving L transpose, and that involves back substitution. So yeah, I mean, it is quite similar. But it turns out it's you're thinking, well, isn't this exactly the same, pretty much what we've been doing, except for one thing. To compute this factorization instead of the customary LU decomposition takes 1/3 n cubed floating point operations, half as many. Why? Because of the symmetry. When you're doing LU decomposition of general matrix, you're computing the lower triangular entries of L, like all those multipliers, and then you're computing the entries of U. You're dealing with the whole matrix. But when it's symmetric, you only have to deal with half of it. So you can cut the number of flops in half. So that's why you really should use this approach if the matrix is symmetric. Now, I haven't said anything about the actual algorithm for LDLT, and it's not something that we're really going to deal with much in this class, since I'm kind of glossing over it. But I do have it in the text if you want to take a look. Okay, so this is what we've just seen. So the starting here is where I show how to derive the LDLT factorization. So you're trying to take the symmetry into account. So it's not just a simple matter of taking ordinary Gaussian elimination and then adapting it to the case of A being symmetric. You don't want to do that because Gaussian elimination would operate on the whole matrix, and we only want to touch half of it if possible. So it really has to be derived from the ground up. So the discussion of all that is takes place here. I won't take the time to deal with this now. But here's the actual algorithm for computing the LDLT factorization. And there is a MATLAB function called LDL that will compute it for you. But an unassigned exploration calls for arithmeticness, but you don't have to deal with that. Okay, and the thing is, if you look at these steps here, it doesn't really correspond to what you're familiar with from Gaussian elimination. It's not the same kind of row operations because it needs to exploit the symmetry. But I'm just letting you know that this thing exists, and that when we have symmetry, there is a better way. But one thing that LDLT and LU have in common is that they don't always exist. You know, may have division by zero, even with a symmetric matrix, if you're doing regular LDLT algorithm. So pivoting is still a thing, but you have to be careful about pivoting because you can just do row interchanges to avoid dividing by zero. You're wrecking symmetry. Whatever you do has to have a symmetric nature. So what that means is if you are going to interchange rows of A, which is equivalent to multiplying A on the left by some permutation matrix P, you must multiply by the transpose of that permutation matrix on the right. So if I'm like swapping rows 2 and 5, let's say, then I must also swap columns 2 and 5. That's what multiplying on the right by P transpose does. So it's a symmetric pivoting scheme that preserves symmetry. So now, instead of like before Gauss elimination of pivoting, you had PA equals LU. Now we have is PA P transpose as its LDL transpose factorization. The way you solve the system of equations, so solve AX equals B, you're solving this system now. And notice you have P transpose times P. This is where I remind you that a permutation matrix P is orthogonal. So P transpose P is identity, so I can just go ahead and stick that in there. So, so the steps are similar for solving AX equals B. Like, just like a Gauss elimination with pivoting, you solve Ly equals PB, you solve a diagonal system, you solve the upper triangular system, and then you have this one last post-processing step where you rearrange the columns of your the entries of your solution W to get your actual solution X. Now, okay, questions so far about how this sort of thing works? Actually, I'm just telling you I'm not really doing it. But it is relevant to what I'm about to talk about, symmetric positive definite. But I can share with you something that, even though I've covered this several times and written about it before, I've never actually bothered to think about until this morning when I happened to be looking at these notes like, okay, what am I covering today? And I just think it's interesting. Okay, what I'm going to do is I'm going to create a new diary. Right. Okay. The effect of symmetric pivoting. What I'm going to do is I need a random symmetric matrix. So first I'll create just any old random matrix. That's 5 by 5. Okay. Now, this is something to keep in mind. Like if you're reading some code and you want to test it, you need the right kind of matrix to test it with. Now we've seen some examples of how you do that already. Like for instance, if you need an upper triangular matrix, you use tri-U or something like that. How do you get a random symmetric matrix? It's actually quite easy. You take A plus A transpose. So in general, for any matrix, any square matrix A plus A transpose is guaranteed to be symmetric. You can take the transpose of this, use the properties of transpose to prove that. So there, now you have a, so this says A has random entries uniformly distributed between 0 and 1. This matrix has random entries uniformly distributed between 0 and 2. Okay, so, and you can see for yourself, like these entries are green, these are green, you get this matrix really is symmetric. Now, let's suppose I want to do symmetric pivoting on this matrix. Now, if I look at the algorithm for LDLT, notice there's a division by diagonal entries again. So what that suggests is we'd like to again have diagonal entries be larger. So it's kind of similar to having small multipliers. Now, so let's suppose I'm going to make a row swap. That's one reason I'm just going to do this arbitrarily. I'm going to swap row 1 with row 4. But before I begin, well, actually, I want you guys to be able to see the original and swap matrices side by side. Okay, so I'm going to swap rows 1 and 4. Then I'm going to swap columns 1 and 4. Okay. So the idea is I'm going to put something else in this 1, 1 position. Okay, so what I'll do is first I'll swap the rows. So rows 1 and 4, all columns equals A rows 4 and 1, then all columns. I'll use the semicolons to not print that out. I don't want to have too much output to sift through. Now the columns. So I do all rows, columns 1 and 4 equals A, all rows, columns 4 and 1. And this time I'm going to leave out semicolons because I really do want to print this out. Now, so here's a modified matrix. And now we have this entry in the 1, 1 position. Look at the original matrix. Where did that entry come from?
The fourth row, fourth column.
Yeah, it came from the diagonal.
Yeah.
So if you swap rows I and j, and then you also swap columns I and j, then that's going to that's going to swap the 2 diagonal entries. Also, if you look at what happened with again, like this entry that was in the row 4, column 1, it doesn't change because of the symmetry. So these diagonal entries, 903.6 and 1.7453, those got swapped. Now other entries were affected, like the other entries in row 1 and row 4. Those changed, but in a way that still kept the overall matrix symmetric. So really what you're doing is, if I want to know, so what I want to do is, if I'm about to start working on column 1, I need to scan the diagonal. I can find the largest entry on the diagonal and then swap rows and columns to put it in the preferred position. So that's one way that you can try pivoting. I honestly haven't taken the time to look into okay, what pivoting strategies do people use, because maybe using partial pivoting or complete pivoting is out the window because you're constrained in what interchanges you can make. It has to be symmetric. So look up novel free plan. Okay. So I just want to show you this is how what happens when you do this kind of symmetric pivoting. Now, if I take a look at the function LDL that computes the LDL transpose factorization. Okay. Now, so this is the default usage. If A already is known to have an LDL transpose factorization, it'll compute it for you. There's no pivoting involved here. But if you take this usage where you get outputs LD and P, so this is the what should be, and it's written a little differently than what I had in the notes. So P transpose AP equals LDL transpose. So the P that you see here is the transpose of a P that you have in the notes. But it's playing the same role that is performing this kind of symmetric pivoting. And just as with the LED composition, you have the option of having a permutation matrix represented as an ordinary matrix, like a scrambling of rows of identity, or as a vector, in which case you have the indices 1 through n that are arranged according to what interchanges were made. Okay. So that's how you could do LDLT in MATLAB. Okay, so questions about LDLT? Okay, now for the remaining part of today. We're dealing with matrices that are not just symmetric, but also positive definite. Now, these are actually very important matrices because they come up in a lot of applications, and they have some very nice properties. So matrices tend to be symmetric, positive, definite, or we just abbreviate it SPD. So it has to be symmetric, and it satisfies this property, that for any non-zero vector x, this expression, x transpose AX, has to be strictly positive. Now keep in mind, what kind of entity is this? A is an n by n matrix. So an x is a vector from bold-face type setting. So I think A times x, that gives me a column vector. But then when we multiply that on the left by x transpose, that's effectively a dot product. So this is the dot product of x with the vector A times x. Dot product is just a number. So this whole expression, A is an n by n matrix, but this whole expression is just a number. And as long as the vector x is, if x was 0, then that number will be 0. But if x is not 0, then this number has to be strictly positive. So that's how positive definiteness is defined. An equivalent conditions, like an if and only kind of thing, is that the eigenvalues of A have to be strictly positive. Now, one thing I hasten to mention is that when you have a symmetric matrix, it's can be proven that all of its eigenvalues are at least real numbers. Because if you have a general n by n matrix A, even if the matrix itself is real, the eigenvalues can be complex because the eigenvalues are polynomial roots. And as you know, a polynomial of real coefficients can still have complex roots. But when it's symmetric, the eigenvalues are always real. Now, because I've talked about eigenvalues and eigenvectors, just refresh your memory on that. What does it mean to have an eigenvalue eigenvector? That if x is an eigenvector and it's x is non-zero, A times x is equal to a scalar lambda times x, and lambda is the eigenvalue. Okay, and then once in a while we'll deal with eigenvalues. It's not really a major focus of this class, whereas in the graduate version of this, in Math 610, I spent a lot of time on eigenvalues, or QR algorithm, that sort of thing.
I thought this was a graduate class too.
Well, okay, 610 is more graduate because it's like not even for undergrads, whereas this one is like mixed. Okay. Now, some interesting properties of eigenvalues, that the determinant of A is a product of all the eigenvalues. And this quantity is called the trace of A. The trace is defined to be the sum of all the diagonal entries. So the trace of a matrix is easy to compute. But it happens to be equal to the sum of all the eigenvalues. Okay, so here's some properties that all symmetric positive definite matrices have. We have a positive determinant, and that's just because the eigenvalues are strictly positive and the determinant is a product of them, so that has to be positive too. All the diagonal entries have to be strictly positive, and the way you can show that is if you take the vector x from a definition equal to a column of identity. So if you do that, then x transpose a x is equal to AII in that case. And by the definition of symmetric positive, this has to be strictly positive. There you go. So this could be, as I'll mention a little later, it's not easy to check, to confirm that a matrix is symmetric positive definite. You can't necessarily tell just by looking. However, this is a quick way to rule out a matrix being symmetric positive definite. Like if you see the diagonal, one of the diagonal entries is 0 or negative, and like, oh, it can't be. But so this is a necessary condition for being SVD. It is certainly not sufficient. Also, whatever the largest entry of A is, an absolute value, it has to sit on the diagonal, so therefore the largest entry is also positive. So it's when you have larger entries off diagonal, that's what we call the matrix to fail to be symmetric positive. And then, because all the eigenvalues are zeros together, so the determinant is positive, we know from that alone that A is invertible, but we also have that A inverse is also SVD, which makes sense because whatever the eigenvalues of A are, the eigenvalues of the inverse are the reciprocals. So the eigenvalues are positive, and certainly the eigenvalues of A inverse are also positive. I remember signing this. I think I signed this as a homework problem in 610. I don't think I signed it here. Well, we'll find out. Okay. So, questions so far about what it means to be SVD? Now, so how can you check if a matrix is SVD? It's actually computationally expensive to do so. So I'm going to bring back a concept that I mentioned recently, the principal minors of A. So when I was talking about the existence of the LU decomposition, the way you would confirm existence is that you would take these submatrices that are called the leading principal submatrices of A. So you'd have the upper left K by K block is a K leading principal submatrix. So to refresh your memory, the principal minors of A are the determinants of these leading principal submatrices. And the LU decomposition exists if and only if all the principal minors are non-zero. So here we have a similar condition. A symmetric matrix A is positive definite if and only if all of the principal minors are strictly positive. So what that means is remember, if the LU decomposition exists, you don't actually need to pivot. It might still be a good idea to pivot just to contain round-off error propagation. But if all the principal minors are non-zero, and therefore LU exists, then that guarantees that you're never going to have a situation where you end up having a diagonal entry equal to 0 when you're about to use that diagonal entry to eliminate entries in its column. That will never happen. So that's also true of symmetric positive matrices because all the principal minors are strictly positive. That the LU decomposition of a symmetric positive definite matrix exists. There's never any obligation to pivot. But just as with a general symmetric matrix, even if it's not positive definite, we don't want to actually carry out Gaussian elimination and LU equivalent to the LU composition. Now we could compute the LDL transpose factorization because of the symmetry, and again, you don't need to pivot. But there's another factorization that's just for it's just for symmetric positive definite matrices. It's called the Cholesky factorization. So the Cholesky factorization has this form: A is equal to G transpose, and the matrix G is lower triangular, and also has positive diagonal entries. So we have existence if and only if A is symmetric positive definite, and it is unique by observing this condition about diagonal entries being positive. So it's kind of similar to LU in that we are still factoring A into a product of a lower triangular matrix times an upper triangular matrix. It's just that because of the symmetry, they are transposes of each other, and because of the positive definiteness, these factors have positive diagonal entries. So if you're going to solve A equals B for a symmetric positive definite, what you can do is compute the Cholesky decomposition, the decomposition here, and then you do forward substitution, like in a general case, with G. And then you do backward substitution with the upper triangular factor, that's G transpose. And then you're done. You have your solution. And just like with LDLT, the computational cost is half that of ordinary Gaussian elimination. It's a 1/3 n cubed flops. Okay. Now, there's a strong connection between the Cholesky factorization and LDL transpose factorization. And if I equate these two, then I can say that G is equal to L times the square root of D. Now, D is a diagonal matrix, so in this case, taking the square root is easy. All you're doing is taking the square root of the positive square root of the diagonal entries. So informally, the LDL transpose factorization is called square root free Cholesky. Now the irony here is when you get to you get to Cholesky factor by taking square root. I'm about to show you the algorithm for computing the Cholesky factorization, and what you're going to find is it involves taking square roots. We don't really like to take square roots because any operation like that, square roots, exponential, sine, cosine, etc., they're approximations, and they require several flops to compute. So normally we're dealing with add, subtract, multiply, and divide. Each one of those is one flop, one floating point arithmetic operation. But a square root or the evaluation of any other function like that counts for several. I honestly don't know how many off the top of my head. But the point is, they're more expensive. So that's why some people prefer to just use LDL transpose because it exists in a symmetric positive definite case. Okay. One thing I want to point out about Cholesky is here I've written A is GG transpose, like a lower triangular times upper triangular. But some authors write the Cholesky factorization this way: A is equal to R transpose R. So here we have a transpose on the outside. Here we have a transpose on the inside, where R, which is just G transpose, R is upper triangular. So it's still lower triangular times upper triangular, but just to know it different. So if you see it somewhere, like, don't get wrong. In fact, I should mention here that in MATLAB you can compute the Cholesky factorization using the Chol function, and if I look at the help page for that, Yeah, so Troll actually uses that over convention. So, well, by default. So if it just has a symmetric positive definite matrix A, and I call Troll on it, it's going to give me R. So A is R will be upper triangular, and A is equal to R transpose R. So the simplest usage of Troll will give you that version of a Cholesky factorization. However, you can call it this way: R is equal to Troll, and then you have, if you specify lower here, then that would be this what I refer to as G in the notes. So you can get either version of a Cholesky factorization, either triangle or lower. Up to you. Now, if you call Troll on a matrix that happens to not be symmetric positive definite, then that will raise an error. In fact, that's what I'm going to do that right now. I'm going to make a matrix that is symmetric. Symmetric, but not positive definite. All right, so this matrix is symmetric. Aij equals Aji. But if I take the determinant of this matrix, I get 2 minus 16. So the determinant is negative. So it's not symmetric positive definite. So if I do Troll of A, yeah, that gives me an error. Okay. Because what's going to happen is if a matrix is not positive definite, the algorithm will break down at some point. So, so effectively, the algorithm is checking for positive definiteness as you go. Okay, question so far about Cholesky. So my advisor at Stanford, and she know that the computer in his office was named Cholesky. So he was on, the whole name was Cholesky.stanford.edu. The Cholesky factorization, I'm going to describe the algorithm a little bit, but besides its usefulness in a computational setting, it's also very useful in a theoretical setting, because if you need to prove something involving a symmetric positive definite matrix, like if that's one of the assumptions, it's very often a good idea to express A in terms of its Cholesky factorization to try to prove whatever it is. And that's something that in a class like 610, I would drill into my students' heads, like if you're proving something involving symmetric positive definiteness, then use the Cholesky factorization. And I ended up getting a comment on my student evaluations at the end of the semester several years ago, and the comment simply said, "When I think positive definite, I think Cholesky." So, okay, well, that got absorbed. Okay. So what is the algorithm? I'll show you using an example. So here we have a symmetric matrix. It might seem odd that this is positive definite. There's a lot of negative entries. But notice that the entries along the diagonal are larger ones. So everything works out. So you can figure out how to compute the Cholesky factorization, like the pattern and all that, by just writing A is equal to GG transpose, where G is lower triangular. And what you can do is you can work out what is the product of G and G transpose, and what are the formulas for the entries. And then you can equate those to the entries in A, and then figure out how to solve for all of these entries. Really, it's just these because the same entries that are over here. So that's what I'm going to do. I'm going to start in the first column. I'm only going to look at the lower triangle of A because of symmetry. So I'll go down the first column and see what I can figure out. So let's get the 1, 1 entry, row 1, column 1. So how do I compute that? using the matrix multiplication and going across the first row and down the first column. But those are mostly zero. So you're going to have A11 is equal to G11 squared plus nothing. So if A11 is equal to G11 squared, then that tells me what G11 is. I just take the square root. So here's why some people went for LDLT, because Cholesky requires square roots. So now we have the 1, 1 entry of my Cholesky factor. Next, we'll go down the column, so the 2, 1 entry. So that's equal to -3. So we'll go across the second row and down the first column. But again, we have all these zeros here. So really, it's just this one product, G21, G11. So this is the relationship I have for a 2, 1 entry. But G11 is known already. I just computed it. So now I can just divide and solve for G21, and I get -1. And that's what happens all the way down the first column. That if I go across any of these rows and down the first column, well, G11 is the only non-zero entry. So, the product ends up being very simple. Or the formulas for these entries in the first column are very simple. And since I already have G11, I just divide, divide, divide. And now I have the first column of my Cholesky factor. So it's 3, -1, 1, and 3. Okay, so questions about getting the first column before I move on to the second column? Right, things get a little more interesting here. For the 2, 2 entry, so 2, 2 entry is equal to 17. So I'm going across the second row and down the second column. So instead of being a square, it's a sum of squares. So I have G21 squared plus G22 squared. Okay. So that's what always happens in diagonal entries. You get a sum of squares. But G21 is known from the first column. So I can take this equation and solve it for the only unknown, which is G22. So all the diagonal entries of the Cholesky factor end up involving the square root of a diagonal entry of A minus certain squares. So the first column, I didn't have anything to subtract off. In the 2, 2 entry, I have 1 item to subtract off. So now I have my diagonal entry, 4, for my Cholesky factor. And then I keep going. So now I'm going down the second column. Now if I look at the 3, 2 entry, so I'll go back up here, and I have row 3, column 2. Now, I'm only dealing with the lower triangle. So my row index is always greater than or equal to my column index. But because of the triangularity of the Cholesky factor, it's a number of non-zero, it's a column that determines how many non-zero products you have. So for the 3, 2 entry, I have G31, G21, plus G32, G22, and that's what I have down here. But once again, everything is known except for G32. We have these from the first column, and then the diagonal entry was computed earlier. So then I have this formula for G32. So I have to subtract. So I'm still taking an entry of A and dividing it by a diagonal entry of G. It's just that I have to subtract something off first. So then I go ahead and do that all the way down the second column, and then I'm done with that. So then I move on to the third column. But when you're the JJ entry of A, is in general a sum of J squares. But all these squares are known except for G33. So again, so you see the pattern going from the first column, just the square root, second column, square root after subtracting off one square, third column, square root after subtracting off two squares, and so on. So the amount of work grows as you move from one column to the next. That's what leads us to the order n cubed process. And then for the only other entry of interest in the third column, it's a product of three terms, but once again, everything here is known except for G43 that corresponds to the entry I'm trying to compute. So I'm subtracting off more and more here too, as I'm from my entry of A before I divide by the appropriate diagonal entry of G. And then finally, the fourth column, there's only diagonal entry to deal with, that's the sum of four squares. Okay, so that's the whole process. So you can see how by equating entries, you can figure out how to solve for everything. And you could fashion together an algorithm from this. Is there any questions about how that unfolded? Another way to come up with Cholesky algorithm is if we have this equation. I'm taking the equation A equals GT transpose, but I'm writing it out entry by entry. So here I only have the IJ entry of A. And this is the IJ entry of what you get from the formula for a product of two matrices. Because AIJ entry is equal to sum over K, and you have first matrix IK, and then second matrix KJ. That's just a general formula. But the second matrix is G transpose, entry KJ, but that's the same as the JK entry of G. So this is another way to look at it. And because we're only looking at entries in the lower triangle, here I have a sum going from K equals 1 to the minimum of I and J. But in the lower triangle of A, I is greater than or equal to J. So this minimum will always be J in that situation. Okay, so actually I'm going to put that in here. Just to simplify things a little bit. Okay. So this right here is just a generalization of formulas that that we see up here, and so these can be used by ordering, like considering entries in order, like one column at a time, and first column, second column, and so forth. That's possible to take this equation and solve it for each entry of G as you go. So that's one way to come up with the Cholesky algorithm. One thing I want to show you the version of the algorithm that's in the text. It's a little different. Okay, so here's a Cholesky algorithm here. There is an exploration where you implement this. I just don't remember if I've signed it, but I think I have. We'll find out. And here you see the square roots to get the diagonal entries. But notice I'm not subtracting off in this case. The reason why is the subtracting off happens earlier. So this carries out the same operations as what I've shown you. They're just ordered a little differently. So that if they're taking square root of a simpler expression. But the general process is exactly the same. Now, so I want to point out, when I write the Cholesky factorization this way, A is equal to G transpose. That's equivalent to this expression right here. A is equal to the sum of these matrices. where Gj, the vector Gj, is the jth column of G. Now, this is a rather unusual expression. A column vector times its own transpose. Now, when you have, if I have a column vector, we assume by default all vectors are column vectors. If I do, for instance, x transpose y, we saw something like that earlier. That's a dot product, that's a number. Also known as an inner product, which makes sense because the transpose is between the two vectors, it's on the inside. Here, the transpose is on the outside. So when you have, so instead of an inner product, which is x transpose y, if you have like something like xy transpose, that's called an outer product. An outer product is a matrix. So here, so in general, a matrix product can be written as a sum of outer products, where the vector on the left is a column of a first matrix you're multiplying. The vector that's being transposed is a row of the second matrix in your product. So this viewpoint gives another way to derive the Cholesky factorization, and that's what leads to the algorithm that's here in the text. So what you can do is, just like in the example, like you go ahead and compute G1. Once you, the first column of G, and that's exactly what I showed you. Now, once you have G1, what you can do is subtract G1 transpose from A. That's what's happening down here. It's taking all that stuff and subtracting it off. And once that happens, well, that eliminates the first row and column of A. So then you work on the remaining rows and columns, like 2 through n. You look at its first column, and that gives you G2. And then you subtract its contribution off. So that's what this algorithm is modeled on. So, okay. Just to let me explain the differences between like what you see here and the process I showed you. Effectively, what it's doing is, like once you compute all of these to get the first column, then go to the other entries of A further down, and these contributions that come from a first column, we just subtract them off immediately. So then when we go to the second column, this has already been subtracted off, so we just take the square root of what's left, and we go from there. One thing I want to point out about this subtracting off, like if I've already computed the first column of G, and I want to update the 4-2 entry, like in this example right here, what do I subtract off? G41, G21. Look at the indices. The column index is from a column I just computed, the first column. Look at the row indices. 4 for this element, 2 for this element, to update the 4-2 entry. And that's exactly what's happening. Here in the algorithm, I've worked out column J of my Cholesky factor, and now I update later entries in later columns by look at the indices. I want to update A, I, K. I have I for the row index here, K for the row index here. Column indexes for both is J, the column I've just computed. Okay. Also notice that K only goes from J plus 1 up to I. Now what that means is I is greater than or equal to K, which makes sense because that's the lower triangle. All details. Okay. Yeah. Oh, yeah, there's the end. That's also the end of this section. So, does anyone have any homework questions or anything like that? I'm mostly caught up with grading.
I need to send you the right stuff.
Yes, yeah. Yeah, I think it's one of the two outstanding assignments. Okay. Right. Oh,
Can you go back to the notes?
okay.
To the very last, yes, here.
Okay. Okay. Well, we have no class on Monday. It's a Mardi Gras break, so the next time I see you will be on Wednesday when we wrap up chapter 3, which, that's all the for midterm. Actually, I want to check here, Canvas. Yeah, sometimes I look at the schedule like, what am I supposed to do today? Oh, yeah, that. Okay, yeah, we only spend one day on that. Okay, then cover only a little bit of chapter 5. Oh, and then, yeah, the midterm is not exactly mid. It's more in the first half of the semester. That means there's less material to study. Okay, so that's what's coming. So, Rich comes.
And you said it's gonna have a time limit this time?
Yeah, so still trying to figure out what that should be, though. I'll let you know soon.